Good evening, everyone. I'm excited to tell you a little bit about Twitter's next generation alerting system. So if you're like me, then getting alerted goes something like this. You're snuggled up, warm in your bed, and your phone starts buzzing on the side table, and it's 4 a.m., and you realize that you've been paged. So this is not a good experience, and it's an even worse experience when it's the result of the alerting system being unreliable. Maybe it's a false alert, maybe the backends are having a problem, and you shouldn't have actually gotten this alert, but now you're awake and it's 4 a.m. So how do we solve this? Well, the most important thing, or perhaps one of the most important things for an alerting system to have, is to be reliable. And related to that, it needs to be scalable, because companies don't stay the same size, they grow, there's more metrics, there's more users, there's more services, and so your system needs to be able to scale while staying reliable. So just to introduce myself, my name's Megan, and I'm a software engineer on the Observability team at Twitter, and I've been there for about 3.5 years. So to give you some context, this is what Observability's alerting stack looks like. So we start at the bottom, the green squares, so that's where your service lives. And then there's a collection agent that lives alongside your service. Next, it exports, sends all of the metrics up that it collects to an ingestion service. And all of those get stored in a distributed key value store that's called Manhattan. It's Cassandra-like. There's a bunch of blog posts that Twitter's done if you're more interested in learning more about Manhattan. We also have a couple of indexing services, the primary one being this temporal indexing service. And then, of course, there's an API layer for users to read back that data, a visualization service with dashboards, some command line tools. But the part of this stack that I'd like to discuss with you this evening is the alerting portion. So alerting command line tools and the alerting service itself. So a little bit more context. This is how Twitter has scaled our metric writes per minute over the time that I've been on the team. So when I started on the team, there were about 300 million metrics that were being written every minute. And we reached a peak last year of 4.3 billion metrics per minute. So that's definitely stressed both the back-end systems as well as the alerting system as it attempts to keep up with alerting on some portion of those metrics. So I like to describe a couple of the issues that our previous alerting system had. There are kind of two main issues that I like to describe. So one of them is that it only knew about its own zone. So that stack that I showed you, that exists in every single zone that Twitter has, and the alerting system only knows about itself and the data in that zone. So if the zone went down or went partially down, network issue, whatever, any alerts that were running in that zone would not escape the data center. So let's say that there were parts of the data center that are down. You still have services that are running there. Are they up? Are users getting 500s? You wouldn't know. So some users solved this by putting alerts in both data centers, or multiple data centers, but then you're getting paged multiple times, which wasn't great. So the other issue was that deployments of the old alerting system were actually impactful. This meant that they were not hot restarting. There would be 5 to 10 minutes of downtime every time we deployed the alerting service. And this was a problem because, like many people, Twitter is looking at continuous deployment, and this made it pretty much impossible to do any sort of continuous deployment for the alerting service. So what were the solutions to these problems? So there are kind of 3 solutions that I like to describe. The first one was around the problem of shards going down or of deployments. So if a shard goes down in the old system, you lose any alert evaluations that were supposed to happen during the time that that shard's down. So the way that we solved that was, as you can see, to store somewhere else, in our case in Manhattan, the alert state and the last time that a successful evaluation happened, so that when the alerts get rebalanced to a new shard, that shard will restart evaluation at the next timestamp that it needs to do. So that solved the deployment problem and the problem of shards going down. So another of the issues that the old system had was that it executed all the alerts that it was assigned, each shard did, linearly. So if the alerts didn't execute within a minute, then some alerts wouldn't be executed. Let's say you have an alert that for some reason, super expensive, use a lot of resources, would take 30 seconds. Well, all the other alerts on that shard only have the other 30 seconds to execute. So the new system actually schedules the alerts fairly, which meant that we were able to reduce the time to detect by 30%, from about 2.5 minutes to a little under 2 minutes. This time to detect is actually from when an event happens on a monitored machine to when the alert is notifying you. So the way that we solved the issue with zone failures or partial zone failures, in the old system, again, if you wanted to be 100% reliable in terms of zone failures, you would need to put the alert in all the zones. In the new system, you simply rebalance the alerts over to another zone when the shards in that zone become unavailable. So those are the 3 solutions that we came up with. And I'm going to share with you our architecture that solved these problems and implemented these solutions. And I'm going to kind of build it up. So the alerting service uses Zookeeper for maintaining the state. And again, Manhattan. And then we have our time series database right there. So the first thing is that the alerting service gets all the configurations. It gets all the alerts from where the configurations live. And then it registers a Zookeeper and says, all right, I'm ready. Tell me what alerts I need to run. There's this balancer process. That's the thing that grabs. It says, OK, what alerts do I need? And there's also this health check service that's running not in the alerting service, but separately, that just checks to make sure that an alerting shard is healthy and up. And if it's not, then it goes into Zookeeper, and for all the alerts that were assigned to that shard, it puts them in a leave state with a Zookeeper ephemeral node. So once the balancer has gotten the alerts that this shard is going to run, it sends that to the alert scheduler. And anytime there's, let's say, the health checks sees that shard 1 left, the cluster, then it puts shard 1's alerts into the leave state. The balancers on the other shards will check and say, hey, look, there's a whole bunch of alerts that need to be executed, and they will be partitioned onto those shards, and the balancer will tell the scheduler to schedule the alerts. So next there's the alert runner. And the way that works is it uses an asynchronous stream for each set of alerts. And so it simply says, all right, every minute I'll read off a timestamp that I need to run this alert at. And so each of the alerts is in its own thread pool, and it has its own stream. So what does the actual execution look like? Well, I mentioned that we store the last successful evaluation and the state. So that's the first thing we do, is read that back. So we read that back and we say, what do we need to start at? What timestamp do we need to start at? So then if we're not taking down the shard, we begin evaluation. We have an alert evaluator. When I started on this project, I thought that was the most interesting part. There's all these other parts to an alerting system in order to do that one main alert evaluation step. So in our case, the alert evaluation step is to go get the data from the data source and run the predicates in that alerting configuration against that data. So we also allow our users to, we have an internal snooze state, so they can snooze things through our UI. And so we read that snooze state out. And once we've attached the snooze data, then we record the alert transition result, if there is one. So again, back up to the current state. If there's been a successful transition, we store in Manhattan that, all right, there was a successful transition at time 2. And then we also record the history into Manhattan so that users can read it back via an API, view it in UIs, that sort of thing. And finally, we notify the user. And then after the end of that has happened, we read the next time that we need to evaluate off of the stream. So our notifier actually offers emails. It hits the PagerDuty API, We also have webhooks, and we're looking into other options as well. So that's kind of the way that our alerting architecture works. For now, I'd like to kind of bring it back to what our considerations were that resulted in this architecture. So the first one was fair alert scheduling. You don't want one person's alerts to cause other alerts to be unreliable. If you have more than one zone, and you think you might have more than one zone, you might want to consider being zone agnostic so that you don't lose visibility in full or partial zone failures. And then catching up alerts, making sure that you can restart shards, or that deploys do not impact the reliability of your alerts. So this system is a lot better than what we had, but it's not absolutely perfect. There are a couple challenges with this system. I think one of them is that the data's in Zookeeper, so any problem with Zookeeper becomes a problem for us. Another is that it is very hard, since the system is so real time, to deal with data that has been delayed. But the thing I would like to discuss, the challenge that I would like to discuss right now is sharding. So we do use this Zookeeper system. We have an internal sharding library that we use to balance alerts onto shards. So how did we decide to do that? I just kind of like to dig into this a little bit. So our system has these abstractions of sets of alerts. It has alerts themselves, and then it has these fan outs. So an alert in the way that we imagine it is a query and some predicates. So the query can have multiple results, multiple time series results. So that's what a fan out is. It's just one of those results, and the same predicates are applied to all the fan outs. So one way that we could have sharded this that might have resulted in very well-balanced clusters, because not all alerts cost the same amount to execute, is to kind of chop and assign alerts per shard. But we actually decided to assign alert sets per shard, which is much easier to reason about, doesn't add any extra complexity to that sharding mechanism. But the downside is we've had to over-provision the cluster a little bit to deal with making sure that the hottest shard can execute within a minute. So that's just a trade-off that we made. So you might want to consider what your data schema is, how you need to shard your alerts, and whether you're going for performance and optimizing on cost, or whether you're more interested in simplicity. So how does the system actually work? Just a couple numbers. So right now it's running about 282,000 alerts, and even more of those fan outs that I described. There isn't really an average number of fan outs per alert. It can be 1, it can be 5,000. And then over the past year that it's been in production, it's had about a 99.94 SLA in terms of uptime. So again, some things that you might want to keep in mind if you are writing an alerting system or considering which one you want to buy, is making sure that the alerts are scheduled fairly, that bad alerts aren't going to impact your alerts. Zone agnostic execution. So again, making sure that zone failures don't impact you. And then catch up of alert evaluations so that you're sure that you get the signal. And finally, sharding strategies for your cluster. Awesome. Questions? Thank you. It's fairly small because it's those 282,000. Those are the number of alerts, so there's fewer of the sets of alerts. So Zookeeper is only storing one piece of information for each of those sets of alerts. There's about 10,000 of those, so 10,000 plus the data for the number of shards in the cluster, which is like 50. So yeah, that's actually a problem that we haven't solved yet. And there's a set of people that would really like us to solve that problem. Right now, our metrics are per, mostly JVM. They're per container. And in terms of getting histograms out so that then you can get an actual view of what the histogram over the entire cluster is, that's something we haven't been able to add simply because with those 4.3 billion metrics, we're kind of dealing with those thus far. But there are some ideas around ways that we could do this, or have it be less of a real time, still get you that data, but slower than the current stack does. In general, getting people to prune their configurations has been a problem for our team generally. I think in the new system, just because it is new, there's less of that. And it is very hard to tell because sometimes people are using the alert notification simply because they want to read it from the API side, so they're not actually sending anything outward. And so we don't know, we can't just say, okay, you don't have any notification configured, we'll just drop your alert, because some people are using it that way. Some people are only using webhooks. So it kind of depends. But again, like for these 282,000 alerts, the cluster is only about 50 shards, so it's not, even if we had to double it, it wouldn't be a big deal. Interesting. I think the main way that people use it for webhooks, really the only way, there might be other use cases that I don't know about, or that are kind of more edge cases, but the main use case is that we have this other system within Twitter that knows about like Puppet and the state of shards. And so you can send a webhook to it and say, restart this, or take some other action, take this machine offline, whatever it is, so that a lot of people use it that way. There's quite a few alerts like that. Actually, one of our largest users is a internal team that watches the health metrics of the whole company, and whose job it is to kind of like be the front line of defense against outages. And so they're like one of our largest users. They have tons and tons of alerts, and almost none of those are paging PagerDuty. They're doing other things. They're creating reports. They're performing actions. Thank you.